Okay, so now everybody's back to the same place. Welcome for those of you who skipped ahead and those of you who followed along. We are now at the point where we want to find and represent our estimators for our parameters in matrix notation. And if you remember, we have the same goal as before. We want to minimize our sampling error, so that's the distance from what we observe, and the true parameter. We want to also minimize our bias. That's the expected value or the expectation of that estimated parameter and that true parameter. We also want to minimize our mean squared error, and that's going to be some combination of our variance and our squared bias. And again, we square the bias because we're not necessarily interested in which directionality it is. And I know this might be a little bit confusing, so I want to walk through each aspect of this. So we can see here that when we're talking about bias, what we're talking about is the estimate of whatever we're interested, usually the mean, right? So is the estimate of our mean close or farther away from the true underlying mean? That's seen in the top left, right? So if it's pretty much on top of it and has a similar center, then that's what we're talking about with regard to bias. When we're talking about efficiency and trying to reduce that error, that's where we're talking about the shape of that curvature. That's what we're talking about when we're talking about the variance element that we're trying to reduce. So there's inherently going to be a trade-off between that in reducing our bias and trying to reduce our efficiency. And hopefully our efficiency will increase as we increase the number of observations. So we also want a consistent estimator, right? So that's why we're trying to invoke consistency, is because often we have very few observations. So we hope that as we increase the number of observations, that's going to increase our efficiency. So now that I've kind of given you the hint or clue that really what's going to help us do that, what's going to be the most unbiased and most consistent and efficient estimator, is going to be when we use our squared residuals. But we need to change from what we did with a bivariate regression and translate that into matrix notation. So if you remember, the way we represented our residuals before was just EI. Now we have a vector of residuals, and again we have our vector y, we have our matrix x, and then a vector of betas that we are going to estimate. We are then going to try to minimize the sum of our squared residuals. We can represent that by our vector E transpose multiplied by our vector E. Again, that's just giving us E squared. This results in y minus x beta transposed times y minus x beta. Now that we have our squared summed residuals written out in matrix notation, we're going to do some calculus, and we want to minimize these sum squared residuals by beta. And I'm not going to get too deep into this, but when we minimize that function by setting it to 0, we end up finding that beta is equal to x transpose x inverse times x transpose x. Now, there's some important things to consider with regard to that vector of betas that we're estimating. Remember that this vector is a linear combination of existing random variables that we have observed, x and y. So they themselves, those betas, are random variables with very straightforward properties, which means that we're going to be able to apply our assumptions from before, specifically the Gauss-Markov theorem. So I want to briefly remind you what those assumptions are. One, our first assumption is that there's a linear relationship. We are modeling a linear relationship between our first covariate and y, our second covariate and y, etc. Second, we are assuming that these covariates are independent of each other. We are also assuming that there is a zero conditional mean, meaning that the errors average out to be zero for any value of our x's for any of the covariates. Fourth, we also are assuming that there's equal variance for all observations in expectation, and that those variances are uncorrelated across observations. So the residuals from one observation are not dependent on the residuals from another, which may be complicated if we have maybe like time dependencies or something. Also, we have to assume that our covariates are unrelated to our residuals. Now, if these assumptions are met just like before, we're going to go ahead and I'm going to prove to you that there's no other linear and unbiased estimator of that true relationship that exists, the true beta parameter that has a smaller sampling variance than the estimate that we have of beta, which is again using the sum of squared residuals. And this is a really important and exciting result. It probably has a less of an impact or momentum on you because in a graduate course, we'd go over other types of estimators and see exactly why this one is best. I'm just kind of giving it to you and hoping that maybe if you're interested, you'll go through the proof. But again, this is an important thing to consider. To begin, I want to show you, remember, our estimate for betas need to be an unbiased estimator of the true underlying parameters. So remember what our equation was from before. Now we're going to take the expectation of that, and when we set it equal to the expectation of our estimate, we see that it'll actually equal the expectation of our estimate itself. Now, I want you to take a second and think about why that's the case. This ends up working out because of that assumption that we had before that our errors in expectation, the average, right, is going to equal zero. So this is great because essentially what this allows us to say is that our estimate and the expectation of that estimated relationship should not deviate in expectation from the true underlying relationship. And if you're interested, you can click on this button at the bottom of the slide to walk through and go through the derivation more concretely on your own. So this may seem kind of like a silly exercise so far, like why does this all matter? And this all matters because one, we want to make sure that we don't have a biased estimate of the true underlying relationship, but two, we want to make sure that we have minimal variance, and that's going to help us calculate our standard errors or our uncertainty around our estimate of the relationship. So we can go ahead and try to construct our estimate of the variance using the sum of squared errors. Now, you'll remember that the equation looks something like this, but there's kind of an extra fold that we need to consider here where these are going to be conditional variances on all of the x's. Remember, we're trying to estimate the variance around a hyperplane in a population since we're going to compare the observed value of y predicated on y, but there's going to be many different values of x. And so we're going to adjust our equation just slightly so that one, our estimate of the variance is the sum of squared errors over n minus k, which is the number of covariates, minus 1. And our estimate then of sigma is just going to be the square root of that, where again, in the numerator, we have the sum of our squared errors. So we want to know the variance covariance of just some of the x's. To find and construct the standard errors, we first need to find the variance of our betas. And again, for now, please just trust me that this is the equation that we're going to use, where it's going to be sigma squared times the inverse of x transpose times x. Now, again, if you want an explanation of how we get to these estimates for the variance, please go ahead and take a look. But again, for right now, just trust me that not only is this the equation, but if this is the equation that we're using for the variance of our betas, this is minimal variance for our estimator of the true parameter. And when we're trying to find the variances for our betas, that's going to be found in a covariance matrix. Remember, we're looking at only the covariance variance for certain terms, and we want to look at our betas. And what I want you to see is what this actually looks like for our least squares. Remember, because we're minimizing our sum of squared errors, this is what it'll end up looking like, where again, the variances of our various betas, like variance of beta 1, variance of beta 2, is going to be along the diagonal, and the covariances are along the off diagonals. And if you remember back to that equation from a couple slides ago, you're going to be able to get the standard errors of each of those betas if you take the square root of the diagonal elements from this covariance matrix.